Perfect. All right, let me know if you guys can see my screen. Just give me somebody just say yes.
Looks good.
Yes.
All right, perfect. So, I've been working on this for a minute. Dr. Seaborn really just helped me out in the last stretch to really kind of help me refine and get very close to a very specific niche problem. And so, I'm talking a lot to you guys about my research, and so here's getting close to the final product. So now, my research that I'm looking for, my research proposal for my PhD is going to be titled "The Implementation of a Graph Network Bundle Adjustment on the FPGA to Accelerate ORB SLAM 2." So to give us a quick introduction, for many real-world applications to computer vision, robotics, and augmented reality related areas, ORB SLAM 2 is the most used visual simultaneous localization and mapping, or also known as visual SLAM algorithm. Currently, the detection and tracking of ORB of 3D objects in real time using ORB SLAM 2 is not accepted to be implemented in a larger system such as an autonomous vehicle due to the computational bottleneck, which will be the completion of the full bundle adjustment. And over to your left, we have a diagram of the ORB2 algorithm. And then the part that's in red is the bottleneck that I'm talking about, the full bundle adjustment. Now, the focus of this research is on design and implementation of a hardware-based graph network system on the FPGA as a solution to the computational bottleneck. So just a quick overview. When I say computational bottleneck, that means that in this entire algorithm, there are three main parts. We have the tracking, the local mapping, and the loop closing. And then at the very end, we have a full bundle adjustment. So what ORB SLAM 2 is doing is taking the keyframes that come out of a stereo, RGB depth camera, or a monocular vision image, and then processing them to create keyframes, which are the most important points off for 3D reconstruction, using those keyframes to then create a local map, using that local map to then loop close, and then go ahead and finish the actual mapping of the area. And then once we get to the very end, the bundle adjustment is the refining of those points. But the bundle adjustment, like I said, is a computational bottleneck, which takes the most time in the whole entire process. So my goal is to minimize that bottleneck by speeding up the bundle adjustment. So before we get there, let's talk about what is bundle adjustment. So bundle adjustment is the objective of to find all 3D point positions and camera parameters that minimize the reprojection area between relative image feature locations. So on my right, I have a diagram of a prism in 3D space, and then I have these cameras that take the different images of the prism from different angles. And so now, using those observations, I want to project and find the 3D points in relative in the 3D space from a 2D image. And so, with doing that, you have a reprojection area that you want to minimize as much as possible, so you get the accurate location of 3D points. So finding this area leads to a nonlinear least squares optimization calculation at each time step. So now we have a nonlinear least squares optimization calculation, and trying to calculate this is what makes this the most computationally intensive and time-consuming part, which is then making it the major challenge for any SLAM-based system. So to really accelerate a SLAM-based system to make it for a real-time application, you have to accelerate the bundle adjustment. So now let's look at how do you even solve bundle adjustment? So now let's look into the Levenberg-Marquardt algorithm. The Levenberg-Marquardt algorithm is actually hold on real quick. Levenberg-Marquardt algorithm is the standard algorithm to solve bundle adjustment. It is an iterative technique that locates the local minimum value of the multivariate function. So now we have a nonlinear discrete optimization function, and we want to minimize that to get the actual value to it that solves the bundle adjustment problem. And there's 5 parts within the Levenberg-Marquardt algorithm. You have the Jacobian update, the Scurry elimination, Jacobi factorization, the cost computation function, cost function computation, and then the gain ratio evaluation. So when trying to go down the bottleneck, you're trying to evaluate, trying to make faster bundle adjustment, you attack the Levenberg-Marquardt algorithm and then attack that algorithm to speed it up as much as possible. So in some of the work that I've done in my literature review, they've seen that the time at the operation within the Levenberg-Marquardt algorithm that takes the most time are the Scurry elimination, Jacobian update, and the cost function computation. So one of the papers in my literature review attacked it by actually doing a speed up and with the FPGA. So to do a speed up example of a bundle adjustment speed up with an FPGA, they took the Levenberg-Marquardt algorithm and used a FPGA SoC, which has an FPGA and also an ARM processor on it, and they put the most computational intensive parts, which would be the square elimination, like I said before, the Jacobian update and compute costs. They put those in programmable logic or the FPGA and ran those in hardware, while then putting the gain ratio and Jacobi factorization in software. So this hardware-software design was used to create speed up for the bundle adjustment. And on the right is an example of the processing element using for the square elimination. So as a hardware engineer, you see that there's a lot of muxes, adders, rams, and multipliers, which are just simple components that we design in our classes today. So that is one way of creating speed up for the bundle adjustment, by taking the most computational parts and putting them hardware using an FPGA. But there are other ways to go about actually creating bundle adjustment speed up as well. That kind of be, instead of actually doing the direct computation, you can use a more of an AI approach and kind of actually learn to do the computation. So that gets into the example of a bundle adjustment speed up with a graph network. So a graph network is a type of graph neural network where the input is a graph and the output is a graph of the optimized values. For this specific problem, this work used input as a graph of camera poses and landmarks. So the initial, at the looking to the diagram on the right, the initial keyframes and landmarks are the input, the graph of that. They go through a graph network block, which is a framework of a graph neural network. And so then they go to that block and they go through multiple graph network blocks to where then the output is in the optimized values of the estimated keyframes and landmarks. And so these graph networks are trained to learn to predict the actual optimized values after they come through from the input graph and give you an output graph of the optimized values. So the graph network also was inspired by the Levenberg-Markov algorithm. So then the nodes and edges are also related to the nodes and edges that were related to the Levenberg-Markov algorithm. So this is just a more fancy artificial intelligence way to actually learn how to do the optimization instead of doing it by hand. So for me, I want to take both of these works and inspire to kind of come up with my dissertation, which would be a combination of both. So then I have my dissertation proposal would be based off of previous work. In the current state of the art, I'm proposing a custom graph network-based bundle adjustment implemented on a commercial off-the-shelf FPGA to replace the current graph optimization G2O in the ORB SLAM2 algorithm. So what does that mean? That means that I'm going to create my own custom bundle adjustment. I'm going to implement that in on a commercial off-the-shelf FPGA, so FPGA that you could buy, and then I'm going to actually use that to replace the current graph optimization G2O squared in the ORB SLAM algorithm, which means I'm going to take out the current graph optimization and replace it with mine. So the novelty within my research is the creation of a custom graph network for bundle adjustment optimization. So this custom graph network is going to be designed by him. I'm not using someone else's code. The idea was inspired from some literature, but the designing of the code I'm going to have to do 100% by myself. So that'll be the novelty within it. I'm going to examine the Levenberg-Markov algorithm, and I'm also going to examine the dogleg algorithm and seeing which output gives me the better results when it comes to the graph network to move forward. And then from there, I'm going to do an FPGA representation of the custom graph network. So actually going through the process of creating the graph network in Python, but then turning that into hardware by using some open source tools along with a hardware high level synthesis tool to get some VHDL and Verilog. And then once I get that, the last part of my research would be the distillation of the graph network for low resource FPGA. So I'm going to run the actual FPGA implementation on the Cyclone 5 to start off, just to get used to actually creating the RTL. But once I actually get the RTL, I'm going to actually use the distillation methods to actually tune it down to get the logic elements down to about less than 16,000 to work on a small Cyclone 10 into Cyclone 10 that's integrates with Arduino board. So there's a custom Arduino board that has an FPGA on it that I want to use to actually be able to run this algorithm, and it's very cheap. It's about $80. So the goal is to put it on a low resource FPGA for cost efficiency. So then here's my methodology. So first, on the left, we have the graph network bundle.
Hold on, pause. That was great, by the way. You did a great job. The only thing, and this is an important little tweak, the reason why you're doing this is for power efficiency. Not cost efficiency. Because cost is, who cares about cost, right?
Yeah.
I'm making a $10,000 drone. I'm gonna spend, as much money as I want on the computer. If I'm making $1 million drone, I'm gonna spend as much money as I want. The problem is you want something that's low power, so that doesn't require all the system and the balance of system in the power rails and connections and things of that nature. So we want a small, compact, low cost. I mean, not low cost, low power. So I would just say swap C, and that way you can incorporate all of that into your explanation.
Gotcha.
Yeah, because that's important to make sure you really drill down. Like, why are we doing this? Like, why are we doing this at all? Ultimately, the reason why we're even doing this work at all is to improve the power efficiency for swap limited um, systems, camera systems, or whatever. But that whole idea is that when you have a swap limited system, you need to optimize for power efficiency.
Gotcha.
All right. Sorry about
No, that was good. It's fine. And then appreciate it. And then now I'll just go into my methodology. So follow my diagram as I go through it, starting on to the left with the graph network bundle adjustment. So how I'm going to create the graph network bundle adjustment, I'm going to actually design it. There's a graph network framework that's open source. And so I'm going to use that and define it in Python, play around with some of the tools and see how I can get the best algorithm between my dogleg algorithm and then also lever my car algorithm. And then I'm going to take that Python code and put it through two stacks. The first stack is the Python, which is takes Python language and converts it directly to C. And then once I have that, I can take it and put through the Intel HLS, so where that I can get a VHDL code from. And then the other stack is that I'm going to take the TensorFlow, take the Python language and convert it and get the TensorFlow XLA. So where then I can use the LaFlow, which is an intermediate open source tool to kind of take the XLA from TensorFlow and help turn it into LMVM to be able to convert it to a high level synthesis tool to get out Verilog. So then I'll come out with two versions of RTL code, Verilog version and a VHDL version. And then after that, so after coming out of the graph neural network, I'll take my RTL that I get and use that to go for FPGA implementation. So now I take the RTL, put it through Intel Quartus Prime, and start working through it to make it to be synthesizable RTL. And then I'll implement that on a Cyclone 5 SoC, Cyclone 5 SoC. And that's a specific number for the actual device that I'm using at the bottom too. And then to distill, I'll take that RTL, synthesizable RTL that I have, and put it through some distillation methods. So really what that means is I'll start actually chopping out and taking out functions that are not completely unnecessary but can be removed and trying to reorder and do some different techniques to be able to get the logical elements down to under 6,000, 16,000, because that's how many resources I have to be able to still see, but still be able to do the job in a high accuracy manner. So I'm going to do that and then put that through Intel Quartus Prime to then make it the synthesizable distilled version of the RTL, and then implement that on the Intel Cyclone 10, which is where the FPGA sits on the board. And so right now, here's my dissertation proposal checklist.
Question, Cameron, question. Can you go back? So this explains what you're going to do for the bundle adjustment. But where is the other code going to be? Is this all going to sit on a board, an integrated board, or is there already memory resources and computing resources that you're going to commit to the other parts of the 3D visualization
So I really
algorithm?
focus on the bundle adjustment just for this sake, but what I really want to do is move forward is run the rest of the code on a low microcontroller called like a Raspberry Pi, and to test it.
I see what you're saying, but here's what I'm saying, right?
Yeah.
You got the bundle adjustment. If you go all the way back to the beginning, go all the way back to the beginning, right here. So this is the end. You got to create a platform in order to figure out how good this code runs, correct? Like, how are you going to test the efficacy of this code without having the entire algorithm stack?
That's what I was saying. So the algorithm stack will run off of Raspberry Pi, and then the input will go through to the bundle adjustment. Sorry, the input, then running the bundle adjustment offline on the FPGA. So that would be the entire system.
Okay, so you have to do that, right?
Yes.
Okay, so you should definitely put that in those other slides.
Okay.
because that's part of your flow. Like you have to go and build that platform on the Raspberry Pi, correct?
Yes.
Okay. So, and that takes a lot of coding, or at least you got to integrate the code you download, and then you got to test it to make sure the platform works using some control bundle adjustment algorithm.
Yes.
Right. So I was just saying that that's actually your first step.
So going here, put it back here. That's my first step here.
Yep.
All right. Okay, I'll make sure I add that.
Hmm. But I
That's
like the way that flowed. It was very clear.
thank you, thank you. So then before I'll do that, but so when I go back and change this, but for right now I have my proposal checklist. So now I have my literature review, where I understand I went through and searched for some the problem and understand the scope of the space. I identified potential solutions, which would be creating a accelerated a graph network using maybe testing out two different algorithms, the dogleg and the 11 per quad. So now it's actually time for me to create the graph network in Python. And then once I create the graph network in Python and evaluate, identify the fundamental challenges that come with actually creating networks. So like the resources, like how many like parts, like what is like with this algorithm, like how is it moving slow and where can I change, like just evaluating that, and then going to then implement the graph neural network onto an FPGA to test. And then after the graph network is implemented on FPGA, implementing the distillation and sparsity methods for low resource FPGA. So actually implementing the methods to kind of cut down the algorithm to fit on a low swap FPGA. And then the last thing would be a system implementation study for swap limited systems. So basically, how would I implement this? How would I implement this method that I have this entire system into a larger swap limited system, such as like maybe like an autonomous car that would have to run this, or like a low power like featured image detector or something along those lines. So this is really my timeline. So then I have, like I said, my literature review completed. I've been out of potential solutions last month, and then right now I'm in the current stages of actually creating the graph network. And then next month will really be identifying the fundamental challenges. That also goes inside with actually defending this proposal right when the beginning of like the middle of August. And then next month timelines would be implementing the graph neural network on FPGA to test in September, then doing some distillation methods in October, and then doing my swap study in November, and then getting ready to defend in December.
Okay, Cameron, go back. Um, that's a very ambitious timeline, but that's fine. You say you're going to start by creating a graph neural network in Python, but I think will be a really good demonstration to do, if it's reasonable to do, is the very first step, where you take your Raspberry Pi and you just take a couple cameras and you just show everyone how long it takes for regular old 3D data capture takes. Like, just run using conventional bundle adjustment. Because what that does is that, one, it gives you a demonstration as a part of your prelim, which is like really cool to have, right? And then two, you've now already built your test bed. You need to now test all your solutions and seeing how it compares. Is that reasonable, or?
Yeah, that's reasonable because I gotta scrape the code off and just put it on the Raspberry Pi and just run it, and then I could just get a low like Raspberry Pi camera that's like less than $40 and just put it to a Raspberry. And I already have a Raspberry.
Exactly. And I would say go and do that. And not only would that will also help familiarize yourself with the code, with the just kind of getting you kind of all up to speed on how this whole thing works. Because you'll have it all built, you'll actually have it tested. And then in your prelim, you can now directly point to how you're going to improve, or what you mean by a swap limited system. Like, you can show that.
Yeah, no, that's perfect. I can do that.
And then so you would just have to shift this timeline down, so such that July, August, that's your first step. And then you get into all the other coding. But once you get that done, I think it's going to give you a lot of momentum to then figure out ways to improve that bundling adjustment at the end.
Yeah, I can do that. And so, yeah, I'll write that down and point that as well too. But other than that, there's my intended dissertation committee that I have. I have Dr. C. Brown, who is served right now as my dissertation advisor. My dissertation chair would be Dr. Gill. Dr. C. Brown's background is electrical engineering, and then Dr. Gill's background is in math. And then for my software like lead to help me out with some of this stuff, I would have Dr. Washington, whose background is computer science. She's also in the Department of Computer Science. And then just for when it comes to, being a principal investigator for, as I want to move forward with this research and for different applications of it, I wanted to have physics background with Dr. Alfred. And then just for my outside external evaluator, for when I get into actually the full dissertation, I wanted to have Dr. April Erickson, who will be my multidisciplinary lead because she works with these type of multidisciplinary systems at NASA Goddard, and I believe that my research could be useful for that in the future. Here are my references, and then thank you. There's my contact, but does anyone have any questions?
I think you did a great job. Everyone, let's give him a virtual round of applause.
Thank you, I appreciate it.
Yeah, I was gonna echo the same thing. I really like the flow of this presentation, and I really like how you went in depth on each of the different topics, especially the graph neural network.
Thank you, thank you.
All right, so can you go back?
Yes. Which slide?
Just go back. Back. Go forward. Go forward. Forward. Where you showing? Yeah. Why don't you put our names? You just didn't put anybody's names.
No, oh my gosh. Oh, that's hilarious. No, so like I had a different slide and like I literally copied all your roles, but I did not put anyone's names. That's hilarious.
Yeah, that would be useful, Also, so can you keep going back? Keep going. You need to adjust the timeline, right?
Yes.
Um, also, so go back to that timeline again. December 2023. I know that's what your goal is, but don't put December 2023 because they're gonna think that's unrealistic, and someone's gonna say something about that. So just put like give yourself a whole year, and then if you finish early, you finish early.
Okay. So what do I do with that? Do I just give like maybe 2 months for each task?
Yep.
Okay. I could do that.
Yep. And if you're ahead of schedule, then that's not a bad thing, right? I mean, this is just a slide, but it just makes the slide look good when it's not like every month you got to hit this. Like, what if you had a snag in any one of the month? Then this timeline doesn't have any flexibility. So, and then make sure you add in the fact that you're gonna build a demonstration kind of a test bed first,
Okay.
right? With the Raspberry Pi. And I think that's really important. Okay, keep going back. Keep going back. By the way, I like the checklist. That was really good. You already know you need to add the first part, the initialization of this methodology. You could literally just call it initialization if you want it, or just like demonstration, or test bed, something like that. Now go back. Keep going. Keep going. This was a great slide. Keep going. So right here, before and keep going one more. Right. So there's a disconnect right here. The disconnect is you really have not fully introduced graph neural networks. So you're missing a slide in between this slide and the next slide where you're going to introduce graph neural networks. So you're going to end this slide by saying this is the latest state of the art. And you have the hardware implementation, the software implementation, but we can use machine learning or neural networks to implement the software part. and get an additional speed up. And then the next slide is, this is graph neural networks. This is how graph neural networks work. This is why it can give me the speed up. And then is this graph. This is how I'm going to now implement this within the flow. But you never actually should, right? Your first time you talk about graph neural networks is you write GN and you write GN block. So I would just, I would add a slide somewhere, or even if you want to put it somewhere on this slide. I don't want the slide to be too busy because I don't want to take away from what you're trying to do here. That's why, but somewhere you need to add a slide that talks about what graph neural networks are.
Okay.
Other than that, I think this is like on point. This looks really good and easy to follow. That's my only question, comment.
Thank you. I appreciate it. So I'll stop sharing real quick, and then I guess I'll